record on this computer, and away we go. Jordan, I don't want to put you on the spot again, but everything worked out with the recording. You were able to get out there and watch that recording after our communication yesterday, correct? I saw you unmute, but then I didn't hear a darn thing. Let me see if my volume is good here. My volume's all the way up. So I did not.
Can you hear me now?
There we go. Yeah. Okay. That's better. Thanks.
Okay. Yeah. I watched it yesterday and took all the notes for it, and then did some of the assignments. So.
Excellent. Very good. Okay. Opening questions before we get going today and start our lecture. Hearing none, away we go. So we were doing some work, working our way towards phasors. That's what we're after. Whatever these phasors are, we're going to figure out what phasors are pretty soon. But we were looking the last time at recognizing the following, that if we had a voltage or a current, didn't matter which one we had, I'll call it a voltage. And if that voltage was equal to, let me just date this on the top. So this is 4/2/2020, makes it easier for us. So if that voltage is equal to V sub m cosine of omega t plus theta, we know that that is equal to the real part of V sub m e to the j omega t plus theta. So remember, when we're looking at the real part of some quantity that's a complex quantity, especially one that looks like the following, if we look at the real part of, this is the way we looked at them before, r e to the j, and I've been using theta, but I'm going to use x just for the heck of it, because it doesn't matter. Whatever multiplies the j in that exponent is what's critically important. And so assuming this r is supposed to be real, don't forget r is a real number, x is a real number. If they're not real, we get into some other ugly situations. This is r times the cosine of x plus j r times the sine of x. So this is what I'm claiming. There's the real part. There's the imaginary part. So x over here is omega t plus theta. It's all of this here. So we know when we take the real part of this, I get the V sub m is the r that's out in front. That's equivalent to the V sub m. So we know that the real part of that exponential is what's on the line above, V sub m cosine omega t plus theta. Then yesterday we said, well, look at this. I can take this quantity and I can break it up inside. And the way I can break it up is V sub m e to the j omega t times e to the j theta. Because we know that all we do is we add exponents together when we multiply by the same base. So e to the j omega t times e to the j theta is nothing more than e to the j, factor out the j, omega t plus theta. So that's the same thing. And then what I want to do is I want to group appropriately, and I want to write it this way. The real part of V sub m e to the j theta, and I want to group all of that. Now all of that multiplies e to the j omega t. And this part here we claimed yesterday when we ended our lecture, this is nothing more than a constant. And I want to make some points about that constant. So let's make some particular points about it. So comments about V sub m e to the j theta. So the first comment I would say is that there's nothing in this that is time variable. V sub m j theta is a constant and does not change with time. So it has nothing to do with time at all. It's completely independent of time. That's an interesting piece of information for us, because when we think about phasors and we think about what we can do with phasors, and we'll figure that out later on, the fact that they are not functions of time, that's going to be pretty important to us. Okay? 2, in general, not always, in general, V sub m e to the j theta is a complex number. Now, there are times when this complex number can be a constant. This complex number can be a constant, a real constant. And this is like the situation we love. When what? Anybody know what the conditions are that cause this complex number to be a real constant? There are 2 conditions. Anybody know what they are? I'll help you with one. When theta is equal to 0, e to the j 0 is just 1. So that complex number just becomes a real constant. Anybody know what the other situation is?
Infinity?
Not infinity. You're thinking about this like it's a real exponential. This isn't a real exponential. It's a complex exponential. So that j is an ugly thing for us. That's the ugliness of that j. Hint, it has something to do with theta. What are the value of theta? Any thoughts? Any ideas? Plus or minus pi. What do we have? What is e to the j pi equal to? E to the j pi. If you're not sure, I'll draw the picture for you. E to the j pi. Well, there's the angle, it's pi. There's the magnitude, it's 1. 1 is the length. Pi is the angle. What is that number?
Zero?
Nope. This number over here is 1. What's this number right over here on this side?
-1.
Beautiful, Jack. -1 indeed. So when theta is either pi or 0, it could be negative pi because they're both the same thing. When we have an angle of pi or an angle of 0, we have a purely real number. That's nice. It's nice to know that. We like real numbers. We're going to want to run into them a lot. Okay. V sub m e to the j theta can be represented in the complex world in both rectangular and polar form. Polar is obviously the easiest, so we need to remember this. Even though it's this v sub m e to the j theta, this ugly looking thing, there are 2 different ways that we can represent that. Here are all 3 of them. V sub m e to the j theta. Easiest one first. V sub m at an angle of theta equals v sub m cosine of theta plus j v sub m sine of theta. So don't ever forget that. We can always go from the polar form to the rectangular form, or from the exponential form to the polar form to the rectangular form. So we have all of that. So what do we know about that? Well, we know from here, this is the amplitude, and this theta is the phase shift. So buried in here are V sub m, the amplitude, or magnitude, depends upon what word you like to use, of the original sinusoid. I'm just going to remind you where that original sinusoid is. Here it is right here. There's the sinusoid. There's the amplitude. That V sub m is still here. There it is. So V sub m it's buried in there. And theta, which is the phase shift of the sinusoid. Now, I said this yesterday, but we were sort of rushing towards the end. So we have and this is what a gentleman by the name of Steinmetz figured out in the early 1900s. So Steinmetz is the one who developed the phasor. And Steinmetz worked for, gosh, I can't remember what company it was. It was an electric company. But what he figured out was that this V and this theta, when you're doing circuit analysis, that's all you need to know. All of this here, this cosine omega t part, it's always going to be there. That cosine is going to be in every current and every voltage. And so there's no need to carry it around. So what we're doing is this phasor analysis is don't carry this around. It's just a lot of dirty work. Don't carry this around. It's always there. So start with it at the beginning and then put it in at the end. At the end of our analysis. So Steinmetz was really, really smart to figure this out. So he began looking at all of this and what is taking place in a circuit. And he said, son of a gun, you know what? What's going to happen in a circuit is I'm going to get if I put a cosine in that looks like this, it is this frequency, omega, everywhere in that circuit, I'm going to get a cosine of omega t, the same exact omega. What's going to differ is the amplitude of the cosine is going to change and the phase is going to be shifted differently. Could be the same, but it's pretty unlikely. So if that's the case, let's just keep track of the magnitude and the phase. Let's not keep track of this part. Let's just put it back in the end. And so he called this a phasor. So the phasor transform. Your book calls it a transform. I don't like that terminology. I don't think of it as a transform. It kind of is, but it's not. It's really more of a form than it is a transform. And so this is what your book says. They call it the phasor transform, and they say the phasor transform of V sub m cosine of omega t plus theta is defined to be equal to, number one, we call it V phasor. And that bar over the top represents that it is like a vector. You've seen us representing in the complex plane, we've been representing these complex numbers like they're vectors. And so we're going to call it a vector. And we're going to differentiate between what is a phasor. Phasors will have vectors, and complex numbers in general will not. We don't put a vector on the top of a complex number. And I'm going to be clear about what this phasor is, okay? So it's going to be V, and then I'm going to write this multiple ways. So it's V phasor is equal to, excuse me as I get my pen here and erase, get rid of that. Okay, it's equal to V sub m, e to the j theta, which is equal to V sub m at an angle of theta, which is equal to V sub m cosine of theta plus j V sub m sine of theta. Depending upon which form you want to use. The form we're going to want to put it in is going to depend upon whether or not I need to add things, subtract them, multiply them, or divide them. Adding and subtracting, we want them in rectangular form. Multiplying and dividing, polar or exponential form is just fine. So there's something that is clearly important here that your author eliminates from the book. So if you're using the book, I want to remind you, this is a phasor that has used a cosine reference. Okay, the phasor has used the cosine reference. There's the cosine right there. Okay, you can choose either the sine or the cosine. I'll go over what that means. You'll see it later. It won't be really clear right now. But in general, again, I'll say a lot of in general. In general, we all use the cosine as the reference. There are going to be times when it's better to use the sine as the reference. So in other words, you can think of the sine as being the imaginary part, the cosine is the real part. We like the real part for a lot of reasons, but we could take the imaginary part as well. So that is the phasor reference. A reference is the cosine. If we chose a sine reference, if we chose a sine reference, if we did, the following would be true. The phasor transform of V sub m sine of omega t plus theta would be equal to V phasor. Notice the notation is going to be the same over here, which is V sub m e to the j theta, unbelievable, which is also equal to V sub m at an angle of theta, which is also equal to V sub m cosine of theta plus j V sub m sine of theta. I want you to notice something. All of that there and all of that there are identical. They're identical. It doesn't matter. You get the same thing for the phasor. The question is, what is it that you're taking the phasor of? Is it a sine or is it a cosine? So in this one, when we choose the sine reference, we have to know that. Here in the first one, when we choose the cosine reference, we have to know that. And so, where did this come from? Right down here. Gosh, I hate when that happens. Okay. Just trying to slide my screen. So this is what we need to know. We're going to start over here in what we call the time domain. I want you to get used to this because electrical engineers always talk about the time domain and then we talk about the frequency domain. And there are a variety of different places where we do this. So we're going to start getting used to this right now. The time domain and then the frequency domain. In this case, When we're in the time domain, we're going to have a function that looks like this. It's going to look like v sub m cosine of omega t plus theta. That's in the time domain. And this transforms, this is the phasor transform or the phasor inverse transform. It transforms into v phasor, which is equal to v sub m e to the j theta. I won't write all of them there. Notice all I carry over that, and I carry over that, and I discard all of this. And I show a double arrow on this because it is a one-to-one relationship. So if I can transfer from the time domain to the frequency domain, I can transform from the frequency domain to the time domain. So for example, if I gave you the following, if I had I1 phasor equals 30 e to the j 10 degrees. Somebody convert that backwards for me and give me the time domain expression.
Uh, 30 cos omega t plus 10 degrees.
30 cosine omega t plus 10 degrees. That's how easy it is. All right? This is a given. This goes there. That goes there. Now, Jack, what if I told you, oh, this phasor over here was chosen with a sine reference? What would you do? So this is with a cosine reference, right? Cosine reference. What if it was with a sine reference? If I gave you this phasor, sine reference, it would be 30 sine, correct?
Yep.
Excellent. And so we're going to choose whichever reference we want to, but we're not just going to randomly choose one. We're going to choose one that makes our work easiest. So that's all a phasor is. It's just I want to write this in words because I'm going to ask you again later on when we get to impedances. So a phasor is a complex number representation of a time varying sinusoid. All right, now I'm going to ask you a question to see how good your thinking skills are. We've done a lot with complex numbers already. Some of you may have liked it, some of you may not have liked it, but we've done a lot with complex numbers. Have any of those complex numbers that we've worked with, have any of them been phasors? Yes or no? If yes, why yes? If no, why no? What's your thought? Have any of those complex numbers been used to represent a sinusoid, or have they just been complex numbers? And all of the work we've done, the homework problems that you're working on, have they been used to represent a sinusoid, or have they just been complex numbers, even though we don't like complex numbers and we're still not sure why they're valuable?
I believe they have.
That is correct. We have not. I don't believe we have. We have not. So now we're in a new world, and we're still going to end up with the same. Ready for this? We're going to get the same complex numbers that we've been using. That's not going to change. They're going to be complex numbers, but they are going to be representative of sinusoids. Now, here's what's weird. On top of that, we're going to use that with other complex numbers that are not representative of sinusoids. Bizarre. And we're going to mix them together. So that's what we're going to see. Okay, let's look at some examples. Let's assume that the cosine reference has been chosen. I want to find phasors for the following. Okay, so we have to pick on 4 different people. First one, V1 is equal to 36 cosine of 3t. Okay, we're going to start, Jack, we're going to start with you since you've been giving some good answers today. I'll help you. It's V1 phasor. Notice the name of the phasor, V1, gets the same name as the time domain function. V1, V1. I just use a capital V1 and a bar on the top. A bar over the top, like it's a vector. It's not a vector, like it's a vector. All right, Jack, help me out. Polar form is fine. Exponential form is fine.
Okay, 2 seconds. I'm going to find my notes on exponential.
Here, ready for your notes on exponential? Follow me. Here's exponential form right here. See me circling it?
Yeah.
It's exponential form right there.
Okay.
Okay?
So we 36
Good.
E to the J theta, but there's no theta.
Would that be correct then?
Yeah,
Okay. What's e to the J0?
just 1.
Oh, that's beautiful. How do you like that? It's just plain old 36. Good. Okay. I2 is equal to 12 cosine 13t plus 45 degrees. Jordan, want to give that one a stab?
I2 phasor
Outstanding.
E. I'm sorry, 12E.
Yep.
J to the 45th.
And don't forget to put degrees in there because it's 45 degrees, not 45 radians. Outstanding. Outstanding. Okay, now I'm going to underline this up top in the problem statement. And then, Connor, I'm going to ask you to help me. So I'll work it out here. IA equals 7 times the sine of 10t. So, Connor, what's the first challenge that we see with this?
It's sine, not cosine.
There you go. It's sine, not cosine, but we said we're using a cosine reference.
Mm-hmm.
You have to convert this to a cosine. So those formulas we gave yesterday, or yesterday meaning our last lecture on Tuesday, so we have to convert this to a cosine. So let me do that. 7 cosine of 10t minus 90 degrees. Is that correct? Did I do that correctly?
Yes.
Good. All right, Connor, take that now, and now give me the phasor. So therefore we have, and by the way, I wrote equals here. That's bad choice. Bad on my part. It's not equals. The time domain is not equal to the frequency domain. It transforms into. So I apologize for that mistake. It transforms into. And this is one way of showing it transforms. Okay, so transforms into here. I'll help you. Go ahead.
So it's 7
Yep.
e to the j, no, negative j of 90 degrees.
Beautiful. Do you know what e to the minus j90 is? Do you remember that? E to the minus j90? If you don't know it, look, go to the complex plane.
J to the 3.
So e to the J90 has, just the e to the J90 has a magnitude of 1, but that's on the imaginary axis. So what is e to the minus J90?
-1.
Negative 1 J, right? It's on the imaginary axis.
Mm-hmm.
Okay, so all this is just minus 7J. Okay? D, V sub x is equal to, let's go 76 sine of 6t minus 150 degrees. Arushi, what's the first thing you recognize there? First thing we recognize, make sure you unmute. First thing we should be recognizing, Ms. Sale, help her out.
Is it the sign?
Absolutely, it sure is. There's the sine, so I need to convert this one to a cosine. Now, to convert to a cosine, we know what to do, so let's do that. So this is 76 sine of 6t minus 150 degrees, and now I just subtract another 90 degrees. Okay.
Would it be cosine at the second one?
I'm sorry, thank you, thank you. Oh, you're so good. Love it. Thank you so much. Yes, it is. Okay, now I'm going to just do my math. So I have the cosine, but I have 150, negative 150 and minus another 90. That's going to give us what, minus 240? All right, what's the next problem? Anybody chime in? What's the next problem?
It's over 180.
Outstanding. It's bigger than minus 180 or a positive 180. So I can randomly add or subtract integer multiples of 360 degrees. So what am I going to do? Add or subtract, and what and how much?
Add 360.
Perfect. Let's add 360. Cosine 6t minus 240 degrees plus 360 degrees. Now that gets me in my range, and that's equal to 76 cosine of 6t plus 120 degrees. Now we're ready to go. Okay, let's now take that, and now let's find that transform. Rishi, back to you. Transform. Let me start it. Vx. So we're going to the phasor transform. What is the phasor? Vx is equal to what? Either you're not listening with us, or you're not unmuting yourself, and you've disappeared from class. All right, Ms. Sale, finish it up. You've done all the dirty work. Go ahead, finish it up.
Is 76 E?
Yep.
Would it be J
Yep.
of 120?
Perfect. That's it. It's that easy. Okay? It's that easy. Just look at this number, and then put that in one of two different forms. By the way, for those of you who are comfortable, and I like this, and I'll use this more than the exponential form, I just do this. Right? It's that number, So for those of you that are still uncomfortable with this complex exponential form, just write it in polar form. It's all good. Now we can expand that if we want to. So some of us are good at expanding. So if we wanted to put it in rectangular form, just to remember, 76 cosine of 120 plus j 76 times the sine of 120 degrees. This is where we need to be good at our sines and cosines. Let me help you. 76 cosine of 120 degrees is minus 1/2 plus j 76. And then the sine of 120 degrees is the square root of 3/2. So we can clean this up a little bit, and we can say this is equal to negative 38 plus j 38 root 3. That's that phasor written in rectangular form. We can write these phasors in any form that we want to. So that's a phasor written in rectangular form. Okay, once we know how to do the phasor, the inverse phasor is really easy. You will not hear me utilizing this terminology a lot. I know it's in your book. And so for those of you who are following along in the book, and some of you are, I just want you to know that terminology that's used there. The inverse phasor transform is just converting. This is how I would say it. So converting from the frequency domain to the time domain. That's what we're doing. We're converting from the frequency domain to the time domain. Okay, so it matters whether or not we have a cosine reference or we have a sine reference. So let's start with assuming a cosine reference. So we'd use a script P inverse, the inverse phasor transform of, I'm going to write it in polar form, V sub m at an angle of theta. We've done it already, so somebody go ahead and tell me what that transform is equal to.
V sub n cosine theta. No, omega t.
Yep, don't forget the omega t. Now, we are going to know what the omega is. Okay, in our world, we're going to know what the omega is, so don't worry about that right now. And then plus our theta. If I chose a sine reference, you get to choose your reference. You're going to choose the cosine reference 99.9% of the time. The inverse of V sub m at an angle of theta would be equal to V sub m sine omega t plus theta. So it doesn't matter which one you do. Okay, so let's look at a simple example. So I have V2 is equal to 3 at an angle of 20 degrees. What is little v2 equal to? All we do is we take that number, 3. Cosine, if nobody tells you, the assumption is always that a cosine reference was chosen. Everybody clear about that? If nobody says anything, it is a cosine reference because that's the standard. So it's going to be cosine. Nobody told me what the omega is, so I have to write just omega plus 20 degrees. Okay, now let's get to a more complete example. Assume that omega is equal to 9 and cosine reference was used. Find the time domain currents and or voltages. For the following phasors. Okay, A. We'll start easy. First person to chime in gets the easy one. 10 at an angle of 30 degrees. Find the time domain current or voltage. Obviously, it's a voltage.
It's going to be 10 cos.
Don't forget the V1, Jack. Good. 10 cos.
And 90
90
plus 30 degrees.
plus 30 degrees. Omega is 9. So there it is. There's the 9. There's the 10. There's the 30. I don't want to make this sound like it's child's play because it's not. This is challenging work. But notice all we're doing. All we're doing here is we're just copying numbers. And then we're putting in the cosine, right? We're just popping it back and taking the 10 and putting the 10 in the appropriate location. We're taking the 30 and we're putting the 30 in the appropriate location. So everything we're doing is pretty straightforward. It's not really difficult at all. Now, it can get difficult, such as the following. B. Ix equals 4 plus J3. Thoughts? Tell me what we need to do.
Need to get it in polar form.
Polar.
Outstanding. Oh my gosh, that was so good. You always have to get it in polar form. Always. So that's what we're going to do. We're going to put this in polar form. Do you remember how to put it in polar form? Do you remember all of our conversions to get these things into polar form? So we're going to start off with, okay, so 4 plus J3 equals square root 4 squared plus 3 squared at an angle of tan inverse of the imaginary of the real, 3 over 4. And I'm going to leave it, 3 over 4. Just leave it like that. I love that. That's beautiful. Built into this is whether or not the angle is positive or negative. Okay, so that is equal to the square root of 25, which is 5, at an angle tan inverse of 3 over 4. All right, we're there. Now, what is the time domain function, current or voltage?
The 5.
Right.
Okay, what before we get there, Connor, what's going to be equal to that?
The current I of X.
Beautiful. Okay. I heard you say 5. Go ahead.
It's going to be 5 cosine of 9t plus the tan inverse of 3 over 4.
Beautiful. Excellent, excellent, excellent. Okay, so this is an example of, darn it, it's not in the form that I wanted. Well, you're going to run into a lot of those. A lot of those, you're going to do your work, and while you're doing your work, you get to the end, and immediately it's not in the form you want. So what you have to do is, if you know you're going to convert back, you've got to make that form be the form that you need to convert back. And we need polar or exponential form to go backwards. Here's one that's a little more difficult, but we're going to see things that look like this. So let's assume that V sub A is equal to 3 plus J6 times minus 2 minus J. So we've got a lot of options available to us. Tell me what option you would like to use. So here's what we need to do. The first thing we need to do is multiply these numbers. So we can do the following. convert each number, each one, this one and this one, we can convert each one into their polar form, then multiply them because it's easier to do that. Or we can just multiply these in the form that they're in right now by foiling it, and then get that one number and convert that one number to polar form. Which do you want to do?
I'd multiply them in rectangular form.
Good choice, Jack. All right, so here we go. So I will do it step by step, just as a reminder. It's been a little while. 3 times 2 plus J6, I'm sorry, times minus 2. J6 times minus 2 plus 3 times minus J plus J6 times minus J. Spell it out. Minus 6 minus J12 minus J3 plus 6. Everybody see those two real terms disappear? And this is simply equal to minus J15, which in case you're not sure is 0 minus J15. Something like this is real easy to convert back if in your head you continue to see this. So I want you to continue to see this. This is minus J15. Can you put that into polar form very quickly? What's the magnitude? What's the length?
Mine is going to be 15.
15. What is the angle measured from the positive x-axis?
Is it 180?
Nope. 180 would be here, Jordan. That's 180. Half of that, what's that angle?
90.
Good, and since I'm going in the clockwise direction or the negative direction,
Yeah, minus 90.
minus 90 degrees. So 15 at an angle of minus 90 degrees. All right? So therefore, we're ready to find V sub A. 15 cosine of 9t, just throw all of that back in there, minus 90 degrees, which coincidentally can be written how? (15 times the sine of 9t), right? That 90-degree shift. It's a sine function. So now we've been working on all of the mathematics on both sides. The mathematics on the side of the time domain, and then the mathematics on the side of the frequency domain. Now, what's going on in this world is, so I want to show you one last example before we take a break. Okay? So one more example. So let's take the following. I'm going to make this up. I'm making these numbers up on the fly. So I haven't calculated this in advance. Times the cosine. I'm going to make them fairly nice numbers as best as I can. Cosine of 100t plus 30 degrees. And I want to take that and I want to multiply that by 2 cosine of 100t. Okay, so I want to multiply those two together. I'm sure you know how to multiply those in the time domain, but you'd end up with something that looked like this. 12 cosine of 100t, cosine of 100t plus 30 degrees, because there's not a heck of a lot more that you can do with that unless you know your trigonometric identities. Watch how you don't need to know trigonometric identities. So I'm going to choose the cosine reference. I know omega is 100, so I'm going to convert. Convert. Here we go. 6 at an angle of 30 degrees, 2 at an angle of 0. Now, yep, leave that there. I don't know why it always wants to do that when I touch my touchpad here. So now I'm just going to multiply those. So I'm in the frequency domain. So I have 6 at an angle of 30 degrees times 2 at an angle of 0 degrees, and I'm multiplying those numbers. So that's 12 at an angle of 30 degrees. So believe it or not, I could have put uglier numbers in here. Believe it or not, when we convert back, now I'm converting back, this is 12 cosine of 100t plus 30 degrees. Okay, don't worry about that. We don't focus on that. We're going to do all of our other work instead in the frequency domain. So the point is there are shortcuts to what we're doing here that allow us to make the work easier. And so in terms of making the work easier, we're going to want to be sure that the work that we're doing is utilizing the appropriate domain, the time domain or the frequency domain. So when we get back, what I'm going to start talking about is how we can look at every circuit element that we've had. So all of our circuit elements, those circuit elements would be, for example, the resistor, the capacitor, and the inductor. And what we want to do is we want to be able to look at those circuit elements, and we're going to look at them in a way that we can use our phasors in the frequency domain to do all of our work. So we're going to take our circuit, convert it to the frequency domain, do all of our work there because the work is easier because we don't have to do differential equations, get our answer in the frequency domain, convert the answer back to the time domain, and then have the solution to the problem. So let's take a 5-minute break. Let's come back in about 5 minutes, and then we'll pick up with that and see exactly how we do that with each of our circuit elements. Okay, so we'll go back now to taking a look at what's taking place in the world of these phasors and how we're going to utilize them with our circuit elements to be able to find shortcut ways of computing the answers to circuits. Now, keep in mind, the restriction is going to be the following. We're only going to use phasors for circuits when we have sinusoidal inputs. So when we have a sinusoidal input, we're going to know that everywhere in the circuit, we're going to have a sinusoid. So the inputs are sinusoids. There's going to be a sinusoid everywhere. Every current and every voltage is going to be a sinusoid. And part of what's going to change is just the amplitude and the phase of the sinusoid, but it'll have the same exact frequency everywhere. And so we're going to use that concept to determine a better way to solve these circuit problems. So here we go. So we need to take a look at these circuits and these circuit elements that we have. So I want to start by looking at the circuit elements that we have and looking at how we can look at what they look like in the time domain and what the equivalent look is in the frequency domain. We always start with the most beautiful element, the resistor. So for the resistor, it looks like that. And nobody is stunned here. I know this is a standalone resistor, but if it was in a circuit, and if there was a current I and a voltage V and a resistor R, we know what the current voltage relationship is. It's V is equal to I times R. We know that. Now here's what I want to do. I want to choose any one of these, the current or the voltage, to be a particular value. So you tell me which one you want me to pick, the current or the voltage.
Current.
Current's a good choice. Here we go. Ready? I'm not just going to pick it to be any value. It's going to be a sinusoid. So I is I sub m. By the way, we use this subscript notation of m. When we don't know the value, m stands for magnitude. It's the magnitude of I. It's a number. I sub m cosine of omega t, whatever omega is, omega t plus theta I. The I stands for the current. Okay, theta I, the phase shift of the current. So I'm just going to randomly let it be equal to that. We know that I phasor will be equal to I sub m at an angle of theta I. Okay, now let's see what happens in the time domain. In the time domain, we have V is equal to I times R. So that's equal to, in the time domain, it's equal to I sub m cosine of omega t plus theta I, all times R. And everybody here knows darn well that we can rewrite this the following way. V is equal to I sub m R, those are two constants, so I'll just group them and bring them out front, times cosine of omega t plus theta I. Excellent. I have a magnitude, I have a phase shift. So if we were looking at V phasor is equal to, in general, it's equal to V sub m at an angle of theta V, in general. But now let's look at what those are. So what is V sub m equal to? What is the magnitude of the voltage?
IMR.
IMR. And what is the phase angle of the voltage?
Theta I.
Theta I sub m R. So this is what we have. When we compare these two, we can see that the current and the voltage are in phase. They're in phase with each other. Their phase shift is exactly the same. So if I were to draw this on a graph, oh my gosh, that was terrible. Excuse that one. Okay, let's try to draw this better. Okay, so one of them looks like the following. We don't know what it looks like, but let's just say it's the voltage, and the voltage looks like the following. And the current is going to have the same exact phase shift, just a different amplitude. So the current might look like the following. Like that. So they are in phase with each other. Really important. Their zero crossings occur at exactly the same spot. They peak at exactly the same location. If this one peaks here, this one peaks there. They peak at exactly the same location. They are in phase with each other. Okay, we can write this very easily. You can see that I can write V the following way. V phasor equals R times I sub m at an angle of theta I. So see if you agree with that. All I did is I factored the R out from the line up above, and a constant multiplier just multiplies the magnitude. Unless that constant is a negative number, then we have to include the phase angle of 180 degrees. But all it's doing is it's just multiplying the amplitude. It doesn't do a darn thing to the phase. Notice it didn't change the phase at all. It just changed the amplitude. Changed the amplitude. That's all it does. So look what's in parentheses. What's in parentheses right there? Very important, equation number 1. So now, in phasor land, in phasor world, when we're in the frequency domain, the beauty is we don't have to learn anything new. V is still equal to I times R, except it's V phasor is I phasor times R. Just like little v was I times R, we have big V is equal to big I times R. So that's our first important relationship. So that means when I look at this resistor in the frequency domain, what we're going to do is we're going to transform our entire circuit. We're going to do more than just a transform of the currents and the voltages that are cosines. We're going to transform everything. So in the time domain, and I don't have colored pens to show you this, this is an R in the time domain. In the time domain, there's my current, it's I, and in the time domain, I have a voltage, and there's my voltage V. In the frequency domain, pretend I'm using a different color pen, this turns to I phasor, this turns to V phasor, and the value here is still R. Right there from that equation. It's still R. So that is a thing of beauty. It is a wonderful, beautiful result. Now we're going to do the inductor. So save that, store that away. The inductor. Okay. Assume this is in a circuit. It's connected to a circuit so that I have a current I have a voltage V, and I have an inductive value L. Notice we continue to do this for the most general of cases. I'm going to select this time, and I'm going to make a very good selection. So this is my selection. Let I be equal to I sub m. I'm going to do the same thing you did the last time. Choose it to be I, omega t plus theta I. Okay? If that's little I, then capital I phasor is equal to I sub m at an angle of theta I. Same as before, no difference. We're randomly assigning to be that. But what we want to know is, what is its effect going to be on the voltage? That's what we want to know. So here's what we need to do. Time domain, I is equal to, V is equal to L, that dot out there looks like a derivative, L times I prime. Okay, L times the derivative of Im cosine of omega t plus theta I. All right, let's see what that derivative is. There's an L. Clearly, I sub m comes out front. Nobody's stunned by that. Then it's derivative of the cosine, which is minus the sine. But there's a chain rule going on, so I have to also take the derivative of the inner, the omega t plus theta I. What's the derivative with respect to t of omega t plus theta I? Derivative of this with respect to t.
Just omega?
Just omega. So here I get the minus, because I get that the derivative is the minus sign. I get a minus omega is going to come out, and then it's going to be the sine of the same function, omega t plus theta I. All right, now right now, that's great. Let me do a couple of things. Let's just pull everything together. Minus omega L I sub m sine of omega t plus theta I. Now the problem with looking at this and trying to see this as a phasor, there are two problems. Somebody tell me problem number 1.
It's a relation to sine and the currents in relation to.
Oh, excellent, Jack. Somebody tell me tougher for you, because we haven't talked a lot about this. Problem number 2. I'll give you a chance to look at it and think about it. But there's another problem. Hint, it's in the amplitude.
Is it because it's negative?
Absolutely. That is correct, Connor. It's because it's negative. We want the amplitude to be a positive quantity. So that was another identity that I gave you the other day with regard to that. So which one do you want to take care of first? The negative sign, or do you want to take care of the fact that it's the sine, not the cosine?
The negative.
Okay, so see if you remember this. Omega L I sub m sine of the same thing plus or minus pi radians, correct? So I'll write it plus or minus 180 degrees. I'm just going to put it in degrees. So if I shift by a sine by 180 degrees, I get the negative sign. So I've just taken care of the negative that was out front. That negative right there that I'm highlighting, I just took care of that. Now, so I'm going to do this one step at a time. Now let's take care of the next thing. It's the sine, and I want the sine to look like a cosine. So omega L I sub m cosine of omega t plus theta I plus or minus 180 degrees. We get to choose which one we want to use there. And then what? Then plus, right? The cosine plus 90 degrees.
Yes.
Is equal to the sine. Is that correct? Cosine plus 90 degrees or minus 90 degrees?
Minus 90.
Minus 90. Got to always think of those. Minus 90 degrees. Minus 90 degrees. So you can see what's going on in here is that I'm going to add these two together with theta I, even though we don't know theta I. So when we don't know theta I, we just want whatever's left to be in the correct range. So what do you think I should choose, the plus 180 or the minus 180?
Plus 180.
Plus 180, yeah. So that'll give me all of this, will just give me a positive 90. So here we go, equals omega L I sub m cosine of omega t plus theta I plus 90 degrees. Very important result. Now let's see why that's an important result. So when we look at this and we say, okay, well, this is my V value, right? This is V. So if that's V is this down here, then V phasor is equal to what? Omega L I sub m. At what angle?
Omega I plus 90.
Yeah, theta I, Jack. Omega is the one that looks like the W in there.
Yeah, my bad.
Okay. It's you know what it is? It's a translation between your language and our language. I knew you'd like that one. Okay, so theta I plus 90 degrees. All right, now, watch this. I'm going to get clever on you. So first of all, you have to tell me that you agree that what I did there is legal mathematically. So we know how to multiply two numbers when they're in polar form. We know we just multiply the magnitudes and add the angles. So is this line here, is line number 1 equal to line number 2? That's what you have to convince yourself. Are those two equal?
Yes.
Great. Tell me what the second term in line number 2 is. Second term.
I phasor.
Excellent, Jack. So that right there is I phasor. Now this one, I want you to look at this carefully, because this is awesome. It's at an angle of positive 90 degrees. It's up here. What's its distance? What's the distance?
WL or omega L.
Excellent. So tell me the rectangular way to write that number, not the polar way. I'll write it, see if you agree with it. J omega L. Anything at an angle of 90 degrees, just put a J in front of it. Anything at an angle of minus 90 degrees, just put a minus J in front of it. So it's J omega L. So here's what we have. Very important relationship for an inductor. So there's something different between this and what we had for the resistor. And here's what's different. Son of a gun, this is a function of omega. So this quantity here is going to be very important to us. We're going to figure out what that quantity is. But I want you to notice that it is a function of L. So it depends upon what the L value is. That's all right. This one over here depended upon what the R value was right there. This one depends upon what the L value is. We'd expect that. But it's J omega L. Now I'm going to show you somewhere over here. This is what I want you to think of. What's the derivative with respect to time of e to the j omega t? I just want you to consider this. Derivative with respect to time. Is that good? J omega times e to the j omega t. I want you to think about L di dt. So if my I looked like that, even though it doesn't look like that, but it looks like the real part of that, when I take the derivative, I get this j omega. That j omega with that L is that j omega with that L right over there. That's where j omega L comes from. Okay, so let me just erase the scratch pad here. So V equals j omega L times I in the phasor world. So if we now draw the circuit element like this, and we say, okay, in the time domain, I have a current I have a voltage V, and I have an inductance L. Down at the bottom, in the frequency domain, I have a phasor I have a phasor voltage V, and what I have here is j omega L. And we're going to see that in a moment. You don't get it yet? Don't worry about it. We'll see it in a moment, shortly. Let's go to our third element. The third element is the capacitor. And the capacitor is just like the inductor. The difference is the V's and the I's. So this one is going to be I, this is C, this is V, and we know I equals C dV dt. So on this one, we knew V was L di dt. So we could do the same work, similar to the inductor. I don't think you need me to do it. But the difference is everywhere there's an I, I replace it with a V. Everywhere there's a C, I replace it with an L. Everywhere there's a V, I replace it with an I. So what are we going to end up with? Here, we're going to end up with, well, let's see what we ended up with here. We had V equals J omega Li. So here we're going to have I equals J omega C times V. We like things to look like the following. V equals. So we're going to write it two ways. 1 over J omega C times I. That's one way to write it. And there's another way that is becoming more and more popular. When I went to school, this was the popular way. Another one that's more popular is V equals minus J over omega C times I. I actually like this much better. Okay, so what does that mean pictorially? Everybody gets that the minus J from this 1 over J over here. 1 over J is equal to minus J. I, V, C, down here, minus J over omega C, V phasor, I phasor. And what we're going to do with our circuits, we're going to convert them from these to these. Time domain to frequency domain to time domain. You're just going to convert back and forth. So we have these three important quantities that we are now going to define. And these are called impedances. So an impedance is defined the following way. So Z is defined to be the impedance, and this is defined to be equal to V phasor divided by I phasor. So when you divide the current, the voltage by the current, you get the impedance. Before, when we divided voltage by current, what did we get before?
Resistance.
Good. Yep. So you're changing your language now. We're in a whole new world, and it pertains to the old world. Everything that we talked about before, we're expanding that to be all-inclusive. It includes capacitors and inductors. It includes everything. And so rather than talking about resistance, we're going to talk about impedance. So Z is V divided by I instead of R is V divided by I. So that is our defining equation, a very important equation as well. Now, note, Z is not a phasor. And I think from an understanding perspective, it's valuable to understand this. So Z is not a phasor, but it's a phasor divided by a phasor. Here's the tough question. Why? Why is Z not a phasor? Remind me to come back to that question. Put it on hold. Let's calculate the impedances of our three individual elements. One, the resistor. So we had we had the following. For the resistor, we had V was equal to I times R. Z is equal to V divided by I. V by R divided by I. Cancel, cancel, equals R. So for a resistor, Z, for a resistor, is nothing more than the resistor itself. So how hard is it to transform a resistor from the time domain to the frequency domain? How hard is that?
Not hard.
Not hard. In fact, what do?
Nothing.
Good answer. Whoever said that. You do nothing. It's just a resistor. It doesn't change at all. That's why we love resistors. Number 2, inductor. We had the following relationship. For the inductor, we had V was equal to J omega L times I. So Z for the inductor is V over I, which is equal to J omega L times I divided by I. Cancel, cancel, equals J omega L. And that is what I drew for you before. So for an inductor, the impedance of an inductor is J omega L. Now I want to go into a different world right now for you. And I want to talk about, so number 1, notice the impedance of an inductor changes as what changes? As what changes?
Omega.
Excellent. So for a DC input, what is the value of omega? It is a cosine with what frequency?
Is it 0?
That is correct. A cosine of frequency 0. What is the impedance of an inductor when omega is 0?
0.
Do you think an impedance would be an impedance of 0 would look like a short circuit? In other words, does that match what we said before about DC steady state? What does an inductor look like at DC steady state?
Sure.
Is a short circuit an impedance of 0? Yes or no?
Yes.
Yes, it is. I want you to think, when you hear the word impedance, I want you to think of everything you thought about with resistance, except it can be complex. And it's better because we can do more with it. So what do inductors not, quote, like? They don't like high frequencies. The higher the frequency, the more the inductor looks like what? I know there's a J in there. Forget the J. As omega gets really large, Z sub L gets large. It's purely imaginary, but it gets large. Well, my gosh, a large impedance is like what? How much current wants to go through a really large impedance?
None.
None. No current. What does that sound like? No current is allowed through.
An open circuit.
Great, great answers. So an inductors don't like things changing fast. And the reason they don't like them changing fast is if you think of the way the inductor is, that changing that current through that thing real fast and causing it to change the magnetic field around it causes a lot of problems. So inductors hate things that change quickly. They don't like that at all. And so the more you try to change things quickly, the harder it is to get anything through there. So an inductor it starts to look like a really large impedance or an open circuit with a very high frequency. That's a problem. That would be a problem putting inductors into all of these circuits of today with the speed of computers, the speed of transmission in communication systems. That's why capacitors are much more important than inductors are for us. Okay, let's go to the third element. The third element is the capacitor. Capacitor, we know for the capacitor that we had V was equal to minus J over omega C times I. So Z is equal to V divided by I. And that's equal to minus J over omega C times I divided by I, cancel, equals minus J over omega C. So what we have is Z sub C for our capacitor. That's equal to minus J over omega C. It is also a function of frequency. If we check this gain and we check DC, remember, what's the frequency of DC?
Zero.
What happens when you divide by 0? You get what?
Undefined.
Good. We call that infinity. Mathematicians call it undefined. Jack, if you keep using the word undefined, we're going to have to change you into a mathematician. It's infinity, which is a really big number. So the impedance of a capacitor, at DC, is infinite. Is that the same as an open circuit?
No.
Infinite impedance, real large. An open circuit, no current will go through it.
Yeah.
Yes,
Yeah.
it is. Okay, so that mirrors our model that we already had for our capacitor. A capacitor with a DC input, it looks like an open circuit. Capacitors don't like DC. But look what happens to the capacitor when omega gets really large. What happens to its impedance or the magnitude of its impedance, even though it's purely imaginary? When omega gets large, the magnitude of Z sub C gets really small. The higher the frequency, the more a capacitor looks like a short circuit. It passes high frequencies very, very easily. Very easily. Unlike the inductor, at high frequencies, it likes to block them from going through. And now you can start to understand how we can make filters that filter out certain frequencies. Pass low ones, let high ones go through. You can understand how that can happen with these elements. So those are the impedances of our three terms. Now, they are functions of frequency with the exception of the resistor. I want to go back to the question that I posed up front. And I want to know, way back here, where is it? Where did I write it? I don't think it was there. I scanned through it. But I asked, why is Z not a phasor? Why is Z not a phasor? I'm just going to go back to the definition of the phasor for you. This is the inverse phasor transform. Here it is. Why is Z not a phasor?
Because it's not a time varying sinusoid.
Outstanding. Was that you, Jordan?
Yeah.
Outstanding. It's not a sinusoid. The phasor is a ratio of two sinusoids, but it's not a sinusoid. It's not a sinusoid. It's not changing with time. Are any of these phases that we just computed? Here, let's go to this one. Let's go to this one here. Does that change with time? Like a cosine?
Nope.
Does it always R for all time?
Yep.
Yep. Same with this one. It's always J omega L. Now, omega could change, but it's not going to in the sinusoid in our circuit. Same with this one. Omega doesn't change. They're not changing with time. They're fixed. Phases are representations of a time-varying sinusoid. So this is just a complex number. That's why no bar over the top. Everybody get that? No bar on the top. They're not phasors. They are time-varying sinusoids. Okay. So that would be my first note. If I wanted to make a note about impedances, my first note would be the following. So notes on impedance. So number one, Z is not a phasor. Even though it's a quotient of two phasors. Steinmetz was a genius when he came up with all of this stuff, as you can imagine. Okay, and it's not a phasor. We'll write it down here. It's not a phasor because it doesn't represent a time-varying sinusoid. Okay. In general, Z is complex. So all we've looked at so far are just an inductor, a capacitor, and a resistor. We didn't talk about what happens when we combine things, like an inductor and a resistor are in series, okay? For a resistor, it is purely real. For a capacitor, it is purely imaginary and negative. It's negative. See this negative sign right there? Z sub C is minus J over omega C. So we know when we have a negative imaginary part, we know that our is capacitive in nature. For an inductor, what can we say about an inductor?
It's imaginary and positive.
Beautiful. It is purely imaginary and it is positive. So that's how we can tell whether or not our loads are inductive or capacitive in nature. And that's an important thing to the power company. We like to do power factor corrections, and you can imagine with a lot of machinery, a lot of motors and what have you, what do you think? Do you think motors are capacitive or inductive in nature? Any thoughts or general feels for that? Hint, a motor has a lot of wires that are wound around a core.
Conductance.
Inductors, correct. Inductors. Yep. Okay, so let's make those observations about what we have. Okay, now, impedances, I'm not going to do this with a proof, in series and in parallel behave exactly the way resistors in series and parallel behaved. What does that mean? Impedances in series do what?
They can be added together.
They can be added together. It doesn't matter if the elements are different because we've put all of them in the same world. They are all in an impedance form now, not a resistor, an inductor, a capacitor. They're all impedances. So impedances in series, they add, and then we know impedances in parallel. Just as a reminder, we have this. 1 over ZEQ equals 1 over Z1 plus 1 over Z2 plus ... plus 1 over Z sub n. So the inverses add. And those inverses are so important, we actually give that a name. We call that the admittance, and we're gonna get to the admittance later on to talk about the admittance. So let's look at an example of what we're talking about. So here's an example of a circuit. And let's just say, don't worry about what I have to the left. I'm making these numbers up, but I want to show you what's really cool. Okay, so let's just pretend I have the following. Let's pretend these have been converted already. Actually, let's do the conversion. Let's assume omega is equal to 10, and let's do the following. And do this is 1/20th, and this is 1/5, and this is, just making numbers up here, 3. Okay? Assume omega is equal to 10. The first thing that we do is we write this in their impedance form. So what's the impedance of a resistor?
It's going to be the resistance value of 3.
I'm going to put the impedances in a box because I don't have colors to show you the difference. What's the impedance of the inductor?
2J.
Okay, and that comes from J omega L for the inductor. So for this inductor, it's J omega is 10 and L is 1/5. And that's where Jack got 2J from. And then the capacitor, reminder, is minus J over omega C. And so that's going to be minus J divided by omega is 10, C is 1/20th. That's minus J over 1/2 equals minus J2. Watch what cool thing I just did for you here. At this frequency, what's really interesting, this is called the resonant frequency of this particular circuit. At this frequency, I can now form a Z equivalent. And here it is. And usually we draw a Z as a box. And so let's see what ZEQ is equal to. This is weird. It's 3 plus J2 minus J2, oh my gosh, equals 3. So this equivalent impedance is 3. In general, do you see how if I change it now to omega is equal to 20, let's change it to 20. So this was omega 1, this will be omega 2. So if it's 20, down here, J times 20 times 1/5, and that's equal to 4j. Over here, minus j times 20 times 1/20th. 1/20th. And now this is equal to minus j. And now all of a sudden, this is minus j. I'll put a circle around it. This one up here is 4j. And now, z equivalent the second time is equal to 3 plus j4 minus j equals 3 minus 3j. Sorry, plus 3j. And if we wrote this in polar form, which we can, this is 3 root 2 at an angle of 45 degrees. Anytime our angle of our impedance is in this quadrant, quadrant 1, if the angle of the impedance is in quadrant 1, it's inductive. And if we're in quadrant 4, it's capacitive. Because the imaginary part is negative here and positive here. And so this has a positive imaginary part. It's inductive in nature. So this second one would look like the following. ZEQ equals 3 plus 3J. And ain't that a thing of beauty? Isn't that awesome? No more, I got to find out. You got to treat them as separate elements. We can add elements that are not from the same family. All of a sudden, we can add elements that are in the capacitive family, the resistive family, and the inductive family. We can add all of those together. Let's put that equation down just so we know. Not that. Yeah, slide down just a little bit. Okay. So here we go. For series impedances. ZEQ equals Z1 plus Z2 plus Z3 plus ... plus Z sub n. So if I had n of them in series, like the following, Z1, Z2, Z3, ... all the way up to Z sub n. And we're looking in here, the old REQ is out of vogue, ZEQ. And there it is. The answer is, just add them up. Okay, let's call it quits for today. Any questions on anything that we've done there with regard to these impedances, et cetera, et cetera? Okay, we're all good with that? So we'll get you an assignment, maybe a partial assignment tomorrow. We'll take a look at what we can do tomorrow as we're finishing up this work in this chapter. We're doing a lot of build-up to be able to get to these sinusoidal steady-state circuits. So tomorrow, you've got those 3 assignments that are due. We've done a lot of those. Those 3 assignments are due tomorrow, and then we'll continue on this chapter tomorrow. Okay? Questions on anything?
I've got a quick question on number 4 in the second order homework.
On the second order circuit?
Yes.
Yeah, that's an ugly circuit, isn't it?
Yeah, I just wanted to know, like, do you need to, I just wanted to know which one you're subbing in to find your equation.
Okay.
My number's a little ugly.
It depends how you do that. Let me get the circuit in front of me. So I know I've got the sheet here somewhere. Bear with me. Okay, 4. Which one am I subbing in? Okay, so first you have to tell me what you did. Did you do one node or did you do 2 equations?
So I did the left-hand side, I did a loop, and then I did a node.
Okay.
I think that's what you put in the question we had to do.
Okay, that's what I recommended that you do. You didn't have to do it that way. I recommended. Okay, so you're looking for an equation for I, right?
Yeah.
So the second equation that you have is going to have an I in it. The equation at the node is going to have an I by itself, and then it's going to have V over 8, and then it's going to have 1/80th v prime, correct?
Yes, that's what I got.
Take that equation, solve for I, and then take the derivative and you'll have I prime.
Okay.
Okay, and then substitute that into the equation for the loop.
Okay, no problem. That's what I did. I got ugly numbers, so I just wondered if I did
Yeah,
it.
I'm sorry about that. I don't know what happened in my calculations, but I solved that circuit problem yesterday and go, oh my gosh, these numbers are ugly. It took me 3 pages to solve that problem.
Yeah, that's.
It's just because the numbers are ugly. Don't get caught up in the numbers. Don't let them bother you. Go through the process, okay?
No problem. Perfect.
Okay.
Thank you.
Other questions? Good for you.
Do you want these assignments due by midnight, or do you want them to do by class time?
You know what? I'd prefer that it was by class time. Do you need till midnight tomorrow, Jordan?
I'm sorry, what?
Do you need till midnight tomorrow?
I mean, I'm trying very slowly to get these done, but like,
If you need till midnight, that's not a problem.
I have the different equation ones done, but it's just working on the circuit ones.
Okay, submit the ones that you have, and then do the circuit ones when you've completed them by midnight. Okay.
Okay, cool.
Perfect. Other questions? Okay, here's my daily proclaim at the end of every day. It's dangerous out there. Be smart. I really care about you. And since they're all men out there today, I care about you guys. I care about you a lot. I'd like to see you back here at school healthy at some point in time. So please be smart. Please be careful and stay away from other people. Okay, we'll see you tomorrow.